All right, I had to again start this recording. So, section 9.1 is talking about confidence intervals, and we're going to talk about a confidence interval gives you an estimation at a certain level of confidence for basically a range of data that will contain the true population mean. The first section focuses on finding this confidence interval when you actually know the population standard deviation. Now the question comes up is, if I know the population standard deviation, why don't I know the population mean? So this type of confidence interval that we're going to discuss initially is not typically used anymore, but to introduce the concept, we are going to talk about this type of confidence interval. Okay, so let's work through. The objectives are to compute a point estimate of the population mean, to construct and interpret a confidence interval for the population mean when the standard deviation is known, understand the role of the margin of error, and we're going to talk about determining sample size. So compute a point estimate of the population mean. The point estimate of the population mean is simply the mean of the sample. So here we have 17 pennies that are minted after 1982, and we want to come up with a confidence interval for the population mean for these 17 randomly selected pennies. To find the point estimate of the population mean, we simply add up all of these weights and divide by 17. So our point estimate is 2.464 grams. So how do I construct and interpret a confidence interval for the population mean? It's an interval of numbers based on a specific level of confidence. So we talk about a level of confidence where if the expected proportion of intervals will contain the parameter if we have a large enough sample. Okay, so the level of confidence is determined by 1 minus alpha times 100. So we typically will have 99%, 95%, 90%, 85%, 80% confidence intervals. Okay, so if we had a 95% level of confidence, if we did 100 different confidence intervals, we would expect that 95 of those 100 confidence intervals to truly contain the population mean, and 5 not to include the population mean. Okay. We construct our confidence interval by taking the point estimate and adding and subtracting the margin of error. And we will focus on calculating the margin of error in a few minutes. Okay. So this margin of error of a confidence interval will estimate of this parameter. It measures how accurate how accurate the point estimate is. Okay. So the margin of error will depend on the level of confidence, the sample size, and the standard deviation of the population. All right, and as we get further into this, we'll see that in our when we're calculating our margin of error, the level of confidence is in the numerator of the margin of error expression. So as that level of confidence increases, so at a 99% confidence interval, we will have a bigger margin of error. At a 90% confidence interval, we will have a smaller margin of error. Now the sample size is in the denominator of the calculation. So as we get a bigger sample, the margin of error will actually decrease because we're dividing by the square root of the number of samples. And the standard deviation of the population is again in the numerator of this expression. And so the bigger the spread in the population, the bigger the confidence interval. Okay. So the mean is that point estimate we talked about before, and the standard deviation is calculated by the population standard deviation divided by the square root of n. And we saw this in Chapter 8. Okay. Because X bar is normally distributed with a known 95% of all sample means will lie within 1.96 standard deviation. So they have a slightly funky way of introducing this. And I'm going to draw you a picture to make more sense. Okay. So here if we did our normal distribution, and okay, 95% confidence interval means that it's going to hit 95% of the data. So remember, the area underneath this curve is 1, so this is 0.95. Now, what's in these tails? Okay, well, that's going to be 1 minus 0.95, which is 0.05, and then we need to divide that number by 2 because it's 0.05 in let me just highlight in both yellow tails together. Okay. So if we divide the 0.05 by 2, we're going to get 0.025 in each tail. Okay, so this is where this idea that we're actually 1.96 standard deviations below 1.96 standard deviations above. And this is where something I discovered yesterday in StatCrunch, was trying to respond to a student's question when I didn't have time to get online, and I just Googled this. I learned something really kind of cool. So let me find, where is StatCrunch? Thought I had opened it. Oh, there it is. Okay, so we know that in the left tail, this area is 0.025. So what I found is we've been using this standard normal calculator, stat calculator's normal. But if I want to find, how many standard deviations below or above, I can actually put in the area. So if I put in 0.025, look what's going to spit out for me, negative 1.96. And if I put in on the other side, and you can see that little area, remember on the other side I'd have to do it differently. I'd have to do 0.95 plus 0.025. I'd have to put in 0.975. So if I put in 0.975 here and I hit compute, it should give me positive 1.96. And then the area over here is 0.025. So you can actually use this normal calculator to find the z-score corresponding to area underneath, which is very useful in Chapter 9. It would have been very useful in 7.1 or 2, but I actually didn't realize you could do that. Found it by accident. Okay, let's go back to our slideshow. So here's a better drawn picture. So that 1.96 corresponds to 1.96 standard deviations below the mean and 1.96 standard deviations above, and that is directly the z-score, okay, for a 95% confidence interval. So for a 95% confidence interval, you can see that you take the point estimate of the mean, and you're going to subtract the z alpha. We're going to call the z alpha over 2 more generically, but in 95%, we're going to do 1.96, which corresponds to the z-score, times sigma over the square root of n, and then on the other side, we're going to add that. Okay, so what we end up getting for this confidence interval is a point estimate plus or minus the margin of error. Now let's look at an example, and then we'll talk about this more generically. Okay, so what they did here is they used Minitab for a simulation, and they did 30 simple samples. Each sample had eight different had 8 different data points in it. So, I mean, they really had 8 times 30, 240 pieces of data. But what they did is they broke them into 30 groups. Okay, and they said here, it's a population that's normally distributed with the mean of 50 and the sigma of 10, which is not as important as what's going on, but they wanted to construct a 95% confidence interval for each sample. So how many of these samples actually result in an interval that contain equals 50? So again, a 95% confidence interval should be that 95% of your samples should actually contain the data, their actual population mean. So if I said 0.95 and they did 30 pieces of data, well, 0.95 times 30, and I'm going to use the calculator on my other computer because you guys could all just put this into your calculator, means that how many confidence intervals should actually contain the true mean, and it's about 28.5. Now here's what's going to happen. We're not going to get 28.5 because you can't get half. It's either going to have the true mean or it's not going to have the true mean. So look, so here's our sample, like sample 8, right here that's highlighted. The mean of sample 8 was 59.62, which means this 95% confidence interval only went from 52 to 66. But remember, we're looking for confidence intervals that contain the mean of 50. That one doesn't. Sample 28, their sample mean was 61.42. And look here, they don't contain 50. Okay. So 28 out of 30 contained it. And this ends up being 93%. But we know we were looking for 28.5, which is not going to happen because you're not going to have a confidence interval that's only halfway in. So this ended up being 93% of the confidence interval. Okay. Now, they're just talking here that if a confidence interval contains a mean, population mean will depend on the sample mean. Yeah. Because if your sample mean is too off, too high, too low, when you add and subtract that margin of error, you're not going to get to that population mean. Okay, and again, 1 minus alpha times 100% confidence interval, that if we had many simple samples of size n and the population whose mean is unknown, then approximately 1 minus alpha, and if alpha was 0.01, we'd have a 99% confidence interval, okay, of the intervals would contain the actual mean. So a 99% confidence interval with a lower bound of 52 and an upper bound of 71, and the upper and lower bounds are just taking the mean, adding and subtracting the margin of error, okay. We can say this phrase, and this is really the key to confidence intervals, okay. We are 99% confident that the population mean is between 52 and 71. All right, so generically, this is how we write out a confidence interval. The lower mean is the point estimate of the population mean minus the critical value of z times sigma over the square root of n, and then the lower bound is the point estimate of the population mean plus the critical value of z, or z of alpha over 2, which we calculated earlier in the semester, okay, and times sigma over square root of n. Now, in order to use a z, the sample size really needs to be larger than 30, or it has to indicate that the population was normally distributed. Okay, so how do we do a 99% confidence interval about this population mean, okay, minted after 1982. So first thing, again, that we already know the mean of this sample because I did this before. Again, that 2.464 comes into play. And how do we know what our z of alpha over 2 is? Well, we could do 99, 1 minus 0.99, which should give us 0.01. Okay. All right. And then remember, the area in our tails is half of that. So it's 0.005, 0.005 here, and 0.005 here. If I go back to StatCrunch, did I lose my calculator? I guess I did. Stat calculators, normal. The z-scores have a mean of 0 standard deviation of 1, so we leave that alone. And we need to find the z of alpha over 2 for 0.005. And I'm going to hit compute. And it's going to give me negative 2.575. So 2.58 would be a good number to use. And let's see what they use on the slide. Here they're just showing that it is normally distributed. They're showing you a box plot. Okay. So they're using 2.575. So they're going out to 3 decimal places. So let's just make that R. So 2.575. Now I could see you rounding to 2.576. And if you're off by a little bit, if you're using this method, just keep that in mind. One other thing is if you went to your formula table card and you went down to table 5, and I know I told a lot of people to print this out. Let's put it way past table 5. Here it is. At the bottom of table 5, let me make this a little bit bigger. The very bottom of table 5, they actually give you the z values for some more widely accepted confidence intervals. So 0.99, 0.98, 0.95, and 0.9. So those are the critical values. So for the kind of standard ones, these 4 standard ones, I would just use the numbers off this sheet. But if it was asking for the z of alpha over 2 of a weird number, let's say, let's do a quick little example. Let's just use this slide. Let's say it wanted the 80% confidence interval, the z of alpha over 2. That's not on the chart. So if I drew myself a picture, I know that this area in between is 0.8. So the area in each tail is 0.1 and 0.1. So I could either look up the negative z value by putting in 0.1, or I could look up the positive z value, which by taking the 0.8 plus 0.1, which is 0.9, because that'll give you the z value for going this way, and then we know, okay, that what's left. So if we go back to StatCrunch, and I deleted this, and I put in 0.1 and compute, negative 1.28. So my z of alpha over 2 would be 1.28. And remember, if I look at it the other way, 0.9, 1.28. Okay, so, and that would be fine to use. Okay, so let's go back. This looks like a big mess. All right, so this lower bound, x bar minus v of alpha over 2 times sigma over the square root of n, and the upper bound. Okay, so we can say that we're 99% confident that the mean weight of pennies minted after 1982 is between 2.452 and 2.476. But wait, there's even an easier way. Okay. And again, they're doing the 99% confidence interval. So let's go back to StatCrunch. Close the calculators. Go to Stat, Z statistics, so we're working with the Z, one sample with summary. The sample mean was 0.464. The standard deviation was 0.02, and the sample size is 17. And I want to do the 99% confidence interval. So when we get to chapter 10, we're going to come in here to do hypothesis testing, but I want to do the 99% confidence interval. And there it is. My lower limit, 2.4515 and 2.476. And it even gives you the standard error. So if you took this standard error and you subtract that from the sample mean, you get this lower limit number. And if you take the standard error and you add that, you get the upper limit. All right, let's go back to our slides. And they rounded. That's why they got 2.52. But stack crunch, software will tell you how many decimal places to round to. All right, so this margin of error is found by taking the z of alpha over 2 times sigma over the square root of n. And they either, in order to use the z, you have to require the population is normally distributed or the sample size is greater than 30. Okay, so let's look at a 90% confidence interval. We can go back to stack crunch. We can actually just go into options, edit, confidence level is 90, compute, and we can see this this margin of error got smaller. The standard it got smaller because the 0.9 confidence interval is going to have a smaller z of alpha over 2, and we can see that here. Oops, I wanted the wrong one. Calculator. Let's go back to our normal calculator so we can visually see this. So when we have a 99% confidence interval, our z of alpha over 2 is going to be 1 minus 0.99, which is 0.01, and then we're going to take that 0.01 and divide by 2, and we should get 0.005. Yep. So I'm going to just put in here 0.05. Okay. And I see that for the, oh, I did the wrong one. Oopsies. So it's 2.575, which is the absolute value of this. Now, if we went to the 90% confidence interval, we do that a little bit differently, remember? Because you do 1 minus 0.9, and then we divide that by 2, and we're going to actually get 0.05. So we're going to change this to 0.05. And then when I hit compute, you can see that the z of alpha over 2 is actually the absolute value of that. It's going to be a smaller number. So by having a smaller number, our margin of error is going to be smaller. Okay. And this is what they're talking about. So the 90% confidence interval, our margin of error has decreased. Okay. And at the 99%, our margin of error is bigger. Okay. Now, what happens if I increase the size of my data values from 17 to 35? And what happens to our margin of error? Ooh, 0.003. So that is smaller than that other margin of error of 0.004. That's not where I wanted to go. There we go. And so they went through the steps and did it. Yeah, so we had a 0.008 something, they rounded to 0.009. So when you have a larger sample size, your margin of error also decreases because that sample size is in the denominator calculation. The larger that is, you're dividing by a bigger number. One last thing, and I don't want to actually leave here, is how do we determine the sample size necessary for estimating the population mean? We came up with this formula. And I'm going to show you where this formula came from. I should be showing this. All right. Okay, so this margin of error, and I don't expect you to remember this, I'm just showing you where it came from. The margin of error is equal to the z of alpha over 2 times population standard deviation divided by the square root of n. So what they're doing is just taking this formula and solving it for n. So if I write it like this, E equals V of alpha over 2 times sigma, you can do that. Because really it's just the V of alpha over 2 and the sigma in the denominator. And so I can either cross multiply, or it looks like I just multiply both sides of the equation by the square root of n. So I have E times the square root of n equals V of alpha over 2 times sigma. I want to get the square root of n by itself. I divide both sides by E. So I have the square root of n equals V of alpha over 2 times sigma over E. And then I want an actual value for n, so I need to square both sides. And that's where this formula came from. There we go. So that's all they do. So you won't be able to use StatCrunch to do this for you. You will have to use this formula, but I just wanted to show you how simple it was. All right, so they give you a margin of error of 0.005 with a 99% level of confidence. Same sigma equals 0.02, so they just plug it into the formula. Z of alpha over 2, 0.575, 0.02, and the margin of error they gave you was 0.005. And then you got 106.09. You always round up to the next highest number, because you can't have 0.09 of a sample. So we're talking about minimum sample size, so you're going to have to round up to the next number. All right. That is all that I have for this recording. I'm hoping, my fingers crossed, that this one actually recorded, and I will see you in a few minutes because we'll talk about 9.2.